In 13.1, we're going to be looking more at planar graphs. We already defined those earlier. To review the definition, a graph is planar if and only if it can be drawn in the plane without any crossing edges. And we looked at the game planarity. So these graphs should all be planar. Move stuff around, try to draw it without crossing edges. There we go. And we beat that level. And move on to the next one. Get something like this. Let's try to solve it. That took an unnecessarily long amount of time. So we can draw those in the plane without any crossing edges. Now, two key examples that we're going to look at are K5 and K33. And let me pull those up in GeoGebra so we can manipulate them. So here we have K5, here we have K33. K5, remember, is the complete graph on 5 vertices. We have all possible edges that we can draw while still having a simple graph. K33 is the complete bipartite graph with 2 sets of 3 vertices each, and drawing as many edges as possible between each vertex to the vertices in the other set. So each of these are going to be degree 3. And then on the right-hand side here, I have K5, but with one edge taken off. So we'll see that that graph is planar, while K5 is not. If we play around with these and just try to move the vertices in such a way that nothing is crossing, you'll find, with some experimentation, that you can get to a point like this where there's just one edge crossing, but we can't completely get rid of these intersections. So some ways of drawing it are going to have multiple edges crossing, but we're always going to have at least one. And we're not allowed to do something like that and just pretend that there aren't edges overlapping there. So this graph, no matter how we manipulate it, appears that we're not going to be able to draw it without having at least one crossing edge. And if we come over here to K33, try to move that around, maybe pull this one over here, see if that will help fix things. As we move these around, we're always going to have at least 2 edges crossing, maybe even 3, depending on how we set this up. So there, actually, it's just one crossing edge, so that's better. But I can't move these in such a way that I have no crossing edges. If I bring this one up here, then we've got a crossing there. Pull it over here, now we've got multiple intersections happening. So we're always going to have at least one intersection of edges where there's no vertex. However, if we take one edge away from K5, which is what we have here, this is now a planar graph. I can move things around. There we go. There's our planar representation of that K5 graph with one edge removed. If we took K33 and removed an edge, so with this representation, if I got rid of this edge between G and F, I would then have a planar graph. So both of those, K5 and K33, appear to have just one edge that's causing a problem, or one edge beyond what we could have without causing a problem. Let's look at some other examples of graphs that we've seen before. Q3, that's our 3-dimensional cube. That is planar. We can have sort of the standard way of drawing that. If we want to make it look 3-dimensional, but we can also have the representation that looks kind of like a square within a square. And that gives us a planar representation of that graph. K23 is also planar. With our standard way of drawing K23, we do have overlapping edges, but we can take that and redraw it like this. I'm going to think of taking one of these 2 vertices and dragging it over to the other side. And it looks something like that. Still bipartite. Our subdivisions are the 3 middle ones, and then the outside 2 are in their own set. But now we have a planar representation for that graph. So our theorem, Euler's theorem, relates planar graphs to these regions that we have in the plane. If we have a connected, simple planar graph, so connected, all one piece, Simple, meaning that we don't have any multiple edges and we don't have any loops. Planar, we can draw it without those crossing edges. And F, the number of faces in a planar representation of G. And so those are going to be the regions into which the plane is divided, which includes an infinite region outside of the graph. So if we look at our K23 example, for instance, we would have one region outside to 3 regions total into which the plane is divided. And so that would be the number of faces then. And Euler's formula says that the number of vertices minus the number of edges plus the number of faces is always going to be equal to 2. Again, for a graph satisfying those conditions. So a corollary to that, if we have a connected simple graph with E number of edges and V greater than or equal to 3 number of vertices, if G is planar, then the number of edges is going to be less than or equal to 3 times the number of vertices minus 6. Now, in that form, that's not maybe the most helpful way of stating that conditional statement. We're saying if it's planar, then something happens. We are probably going to be given a graph and trying to determine whether or not it is planar. So the contrapositive is going to be more useful. Taking the contrapositive, we'll have the negation of this conclusion. So if E is greater than, strictly greater than, 3V minus 6, then we know that the graph is not planar. Second part, if G is planar, then there's going to be a vertex of degree less than or equal to 5. Again, we probably won't know if the graph is planar, so the contrapositive will help us to determine, at least to say that something is not planar. If the degrees of all the vertices are greater than 5, strictly greater than 5, then G is not planar. And then finally, if G has no cycles of length 3, in addition to being simple and connected with 3 or more vertices, then if it's planar, the number of edges is going to be less than or equal to 2 times V minus 4. So we get a tighter bound than we had in part 1. Instead of 3V minus 6, we now have 2V minus 4. So given a graph where there are no cycles of length 3, if the number of edges is strictly greater than 2V minus 4, then we know that G is not planar. So these contrapositives are going to be the more useful way of stating it. Keep in mind, if these conditions are not satisfied, then we can't say anything one way or the other. For instance, in part 3, if E is less than or equal to 2V minus 4, then I cannot say that G is planar. We're not allowed to use the inverse or the converse of that statement, whichever one you're looking at. Similarly for the other parts. If we do have cycles of length 3 and we're using part 1, I can't conclude, if I go through calculate this for the inequality, if E is less than or equal to 3V minus 6, then I can't say anything one way or the other about the planarity of G. And similarly here, if I have vertices whose degree is less than or equal to 5, then it doesn't mean that G is necessarily planar. It may be, it might not be. So let's look at K5 and K33 and see if any part of that corollary will apply here. In K5, you can go through and count, but the total number of edges is equal to 10, and we have 5 vertices. It's a complete graph on 5 vertices. So let's go through each part of the corollary and see what we can say with that. So we're going to determine whether or not 10, the number of edges, we want to know if that's greater than 3 times the number of vertices, so 3 times 5 minus 6, well, that's going to give us 15 minus 6, which is equal to 9. So that is true, which means that we can conclude that K5 is not planar. Let's try the second part, see what we can say there. Well, here, the degrees of all the vertices are equal to 4. Look back at K5, we have each vertex with an edge going out to all of the other 4 vertices. So we have all degree 4 vertices. So that means that that part is going to be inconclusive. And again, it's important to note that it is inconclusive. I can't say anything one way or the other. So if I'm only applying part 2 of that corollary, then I cannot claim that the graph is either planar or non-planar. I have to use another test. If we look at number 3 in K5, Let's go back to this representation. Well, we do have cycles of length 3, and so we're not going to be able to use that part. So that one's not applicable. If we look at K33, the number of edges is equal to 9, and the number of vertices is equal to 6. We have 3 plus 3 vertices. You can go through, count the number of edges from each of the 3 in one set. We have 3 edges going out to the 3 vertices in the other set. So we'll have 3 times 3. Gives us 9 total edges. So let's go through and check each part of the corollary. First, for part 1, we're going to see if 9 is greater than 3 times 6 minus 6. It's going to give us 18 minus 6, which is 12. Well, that is not true. So that means that this part is inconclusive. Again, inconclusive. We cannot say anything one way or the other there. Part 2 of the corollary, looking at the degrees of the vertices. Well, all of these have degree 3, so that part is also inconclusive. And then looking at part 3 of the corollary, we need to make sure that we don't have any cycles of length 3. And justifying that may be a bit difficult. For this one, we'll just accept that we've gone through and sort of brute force checked. As we travel around and try to complete a cycle, we're going to have basically all of these sort of isomorphic to each other. We'll have at least 4 edges that we have to travel along to get back to where we started. We could make it longer than that, but we're going to have at least 4 edges. If I want to go from J back to J, length 4, F back to F, I'm going to have at least 4 edges that I traverse to do that. So it does apply, and then we can look at E, so 9, compared to, in this case, 2 times 6 minus 4. So we're going to get 12 minus 4, which is 8. And 9 is greater than that. So we can use part 3 and conclude that K33 is not planar. And it turns out that K5 and K33 are basically the smallest non-planar graph examples that we can find. And Kuratowski's theorem, which we'll look at next. Let's go ahead and state the result first, and then we'll define some of the terms. A graph is non-planar, not planar, if and only if it contains a subgraph homeomorphic to either K5 or K33. So even though the previous corollary didn't give us information in both directions, we had inconclusive cases there, this statement is if and only if. So if I can find subgraphs, find basically a copy of K5 or K33 hiding out in our larger graph, then we can automatically conclude that it's non-planar. Now, it's not just a subgraph, but a subgraph homeomorphic to one of those. Well, what does homeomorphic mean? 2 graphs, G1 and G2, are homeomorphic if and only if they can be obtained from the same graph by a sequence of what are called elementary subdivisions. What's an elementary subdivision? Well, we'll define that up here. An elementary subdivision of a graph is an operation whereby we remove an edge and add a vertex and these edges. So the idea here is that we're going to have an edge between U and V. Say, there's U, there's V, edge. And then we're going to remove the edge between the vertices. So we just have U and V. And then we're going to add a vertex W. Sort of think of putting it in between. And then we're also going to add edges from U to W and from W to V. Now that's sort of a roundabout way of basically saying that I'm going to take this edge and I'm going to basically cut it by inserting a new vertex on that edge. So either by placing that vertex there in G1 and G2, they're homeomorphic if and only if they can be obtained from the same graph by some sequence of elementary subdivisions. So we can get from one to the other by performing these subdivisions. Or in some cases, there may need to be a third graph that we start with. Maybe we can't go exactly from G1 to G2 with these sorts of subdivisions, but there was a third graph from which they both could be obtained with those elementary subdivisions. So, for instance, if we have, let's say, that as our starting graph, then I can perform elementary subdivisions on that. Let's go ahead and just make a couple copies of it. I can start making elementary subdivisions. Let's say I put an edge there, put an edge there, put one there. And on this graph, maybe I split both of those. So these can both be obtained from this graph by performing elementary subdivisions. If I were to, and I could get, I guess, from this G2 to G1, if that's how I want to label those, via an elementary subdivision. I can't go from G1 back to G2. I can't remove a vertex in that sense. But I could just say I'm starting with one that already had it removed and then say that they're homeomorphic in that way. So a graph is non-planar if and only if it contains a subgraph homeomorphic to either K5 or K33. So I could just draw something. I'm going to think of maybe starting with K5 and then adding some edges and vertices to that. So there we go. There's our K5, and now we'll start doing some subdivisions. Maybe I have some additional vertices that weren't part of that to start with, and we'll throw some edges in there, make it all connected. So it may be obscured. I could take these and start to shift them around, but we're looking for that subgraph that is homeomorphic to either K5 or K33. So given this, we would want to try to identify that underlying copy of K5 that's floating around in there, or at least something that's homeomorphic to K5 floating around in there. Now, one application that the book then goes on to talk about is how planar graphs are related to these geometric objects called regular polyhedra. I'm not going to go through the details of the derivation here. The book talks through it, but essentially they're starting with Euler's formula and then using other facts that we know about how the number of edges and degrees and vertices relate to each other, setting up an inequality, and then finding values that satisfy those inequalities. So looking at all the possible combinations and then putting them together. And it turns out that there are 5 combinations that satisfy the inequality, and those relate to 5 what are called regular polyhedra. So a polyhedra is this 3-dimensional shape. It's going to have a regular polygon for each of its sides, and a regular polygon is a polygon where all of the sides and all of the angles are the same. And in a polyhedra, we're going to have all of these faces coming together, and the corners that are formed here are the vertices. The number of faces that meet at any given vertex is going to be a defining characteristic. And these are also going to have additional properties. You can tile 3-dimensional space with these, so you could fill 3-dimensional space completely with these shapes without leaving any gaps left over. Let's look at maybe a rotatable view of these in Mathematica, and also some examples of irregular polyhedra. So here is an irregular one with, this has 30 faces to it. So each of these little things is a face. Spin that around, see what's going on there. Let's bring that down a bit. Let's say we have 4 faces on that, so we could count. We've got 1, 2, 3, and then back here is the 4th one. Rotate that around. But these are not regular polygons on the sides here. They don't have the same side length, and the angles are not necessarily all the same. Now this is Mathematica just coming up with one. We could ask for something with 100 faces if we wanted to, something like that. At each vertex, at each of these corners, we can count how many faces are coming together. So here we have 1, 2, 3, 4, 5 coming together, and that should be true at any corner that we're looking at, except over here, 5. I'm not getting a good view, so there might be something I'm not seeing in there because of how this is angled. And since these aren't supposed to be regular, that actually may not be true in general. So for irregular polyhedra, we're not going to have the same number at each corner. For the regular ones that we're looking at, though, that is going to be a defining characteristic. Yeah, so here we can see that we have definitely more than 5 coming together at that particular corner point. If we look at our 5, so we have the tetrahedron here. Spin that around. So we have those 3 equilateral triangles making up the sides. Looking at just the cube, there we have 4 sides on each. 5 is the dodecahedron. You can spin that around. So we have all these pentagons coming together. At each vertex, we've got 3 faces coming together on that. Then the octahedron has 8 sides total. See that? And then the dodecahedron.
Here, spin that around and see that.
So then because these are derived from Euler's formula, then they are all going to have a planar graph that relates to them. And the idea here is that we're going to draw all of the vertices and the edges connecting them, but we're just going to draw it in the plane instead. So for the cube, we're actually going to get our Q3 graph for that. For the tetrahedron, that's going to be our W3. So we have that wheel. The book also describes this as thinking of sort of looking through a hole in one of the faces and then drawing what you see and sort of imagining yourself in the infinite region outside is what that picture would look like. I won't ask you about the derivation that gives these, but you can look through that in the book to get the restrictions that tell us that there are exactly 5 of these.